Hi, and welcome to my channel and to the first video of this series exploring landmark experiments in protein science, based on my book of the same name, which can be purchased on Amazon, and that link is in the description below. Despite the fact that this is a series on the history of cell biology, I will start with a short primer on the history of chemistry since all living processes are chemical in nature, and this will also give adequate background for those of you with limited knowledge in chemistry, and will hopefully help you understand certain things I'll be going over in later videos. Besides, the history of chemistry is exciting in its own right, and I suggest you check out the books I've included in the description below. Although fire was discovered 300 to 400,000 years ago, the chemical mechanism by which this occurred was unknown until relatively recently. Plato suggested that all burnable matter contained a mystical flammable principle, which alchemists later suggested to be the spirit of sulfur or maybe sulfur itself. Paracelsus, a prominent 17th century alchemist, suggested that if something could be burned, it was because it contained sulfur. If it gave off a flame, it was because of its mercury, and the ash it left behind was due to its salt content. However, John Becher, who had observed the burning of things that did not contain sulfur, suggested an alternate hypothesis. All things that burn contain a terra pinguis, an inflammable earth that allowed them to burn, which he called phlogiston. Becker explained that when a substance burned, its phlogiston was given off in the form of a flame and transferred to the atmosphere. So if something wouldn't burn, it was simply because it didn't contain any phlogiston. And burnable also included the vital act of breathing, for did not the lungs constantly exhale phlogiston as food was consumed during digestion in human and animal bodies? Many chemists who weighed matter before and after it was burned found that the ashes left behind weighed less than the original, and this proved the existence of phlogiston in the eyes of many. But many others found that the ashes actually increased in weight, to which Becker replied, "Yes, you fools, but don't you know that my phlogiston may sometimes possess the power of levity? It weighs less than nothing. Naturally, then, the ash of your metals weighs more than the metals you burned. Something minus another thing which weighs less than nothing weighs more than that original something." Obviously, there was some rationalization going on here, but phlogiston still persisted for more than 200 years because it seemed to explain many things that chemists struggle to explain. Metals turned into powders when burned because they lost their phlogiston. The metallic properties of powdered metals were instantly restored by the addition of charcoal, a highly inflammable substance because it transferred its phlogiston to the powder. And although phlogiston turned out to be wrong, it served an important purpose in the story of chemistry, and in science as a whole, in that it urged chemists to investigate and determine the true mechanism of the phenomenon of fire. So a century later, an English natural philosopher called Joseph Priestley was writing a book on the history of electricity and endeavored to ascertain several facts which were disputed, and this led me by degrees into a large field of original experiments in which I spared no expense that I could possibly furnish. At the time, gases liberated during chemical reactions were clumsily and inefficiently collected in opaque balloon-like bladders, so Priestley improved this method by filling a glass bottle with mercury and inverting it into a vessel that also contained mercury. A solution which evolved gas was then placed in a bottle, and the emitted gas was bubbled through the mercury via a tube covering the mouth of the bottle. And as the gas was evolved from the solution, it displaced the mercury in the bottle, and the gas was trapped between the mercury and the bottle. And using this apparatus, he endeavored to extract air from Mercurius calcinatus per se, a red powder obtained from heating mercury, which had been done many times before and, as expected, found that the air was expelled from it readily. But on this particular day, he wondered what would happen if he placed a lit candle inside the bottle containing the expelled air, wholly expecting that it would be put out. But to his surprise, he found that the candle burned in this air with a remarkably vigorous flame, and it consumed very fast. And since the air readily accepted the phlogiston that was expelled, he hypothesized that this air, which he called dephlogisticated air, accounted for the vital powers of the atmosphere. And so Priestley set out to determine how wholesome this dephlogisticated air really was. So he performed what I imagine was the first mouse study ever conducted, and captured mice from around his home and put it into a glass vessel containing 2-ounce measures of the air from Mercurius calcinatus, so dephlogisticated air. Had it been common air, a full-grown mouse, as this was, would have lived in it about a quarter of an hour. In this air, however, my mouse lived a full half hour. So he suggested that the extent to which air was breathable depended on the amount of phlogiston in it. And so based on this, combustion needed two things. First, the item to be burned had to have phlogiston in it, and second, the atmosphere surrounding it had to have the capacity to accept phlogiston when it was released from the burning substance. Therefore, dephlogisticated air was pure and allowed for an increased capacity for combustion. He even decided to try dephlogisticated air for himself and reported that my breast felt peculiarly light and easy for some time afterwards, and suggested that, in time, this pure air may become a fashionable article in luxury. But he also warned that as a candle burns out much faster in dephlogisticated air than in common air, so we might, as may be said, live out too fast, and the animal powers be too soon exhausted in this pure kind of air. A moralist at least may say that the air which nature has provided for us is as good as we deserve. In 1766, shortly before Priestley's experiments, Henry Cavendish published his experiments with airs and reported that metals dissolved in a variety of acids, with the exception of nitrous acid, all produced a highly flammable type of air which exploded loudly when subjected to a flame. He also found that the loudness of the explosion and the size of the flame depended on the ratio that this air was mixed with common air, and that this new air was more than 10 times lighter than common air. Since all the flammable air generated by metals had the same characteristics, that is, that the explosion they caused and their density were identical, Cavendish concluded that it seems likely from hence that when either of the above-mentioned metallic substances are dissolved in acidic solutions, their phlogiston flies off without having its nature changed by the acid and forms the inflammable air, but that, when they are dissolved in nitrous acid, their phlogiston unites to part of the acid used for their solution and flies off with it in fumes, the phlogiston losing its inflammable property by the union. 20 years later, in 1784, Cavendish was inspired by Priestley's experiments showing that the walls of a glass vessel became covered with dew when flammable air was subjected to an electrical spark, and determined that almost all the inflammable air and about one-fifth of the common air are turned into pure water. He also repeated this experiment in which dephlogisticated air was mixed with flammable air and found that, when they are mixed in the right proportion, very little air remains after the explosion, almost the whole being condensed. It follows that almost the whole of the inflammable and dephlogisticated air is converted into pure water. Therefore, water consists of dephlogisticated air united to phlogiston, and that inflammable air is either pure phlogiston or else water united to phlogiston. At the same time Cavendish was working in his laboratory, another prominent scientist, the Frenchman Antoine-Laurent de Lavoisier, who would later be known as the father of modern chemistry, was performing his own series of experiments when he repeated one of Priestley's experiments in which mercury was constantly heated for 12 days until the calcination of mercury did not at all increase, and confirmed that the air was no longer fit either for respiration or for combustion. But Lavoisier noticed that some red granules had been left behind, so he collected them and placed them into a small glass retort, having a proper apparatus for receiving such liquid or gaseous product as might be extracted, and reapplied fire until the retort became almost red hot, at which point the red matter began gradually to decrease in bulk, and in a few minutes after it disappeared altogether. And so this is the setup in question. He placed the small red granules in the retort here and used the furnace to heat them up, and the air generated was collected as usual over the liquid in this jar. And when he analyzed this air, he found that it was greatly more capable of supporting both respiration and combustion than atmospherical air. This was the same air that Priestley called dephlogisticated air. Lavoisier summarized these experiments this way. In reflecting upon the circumstances of this experiment, we readily perceive that the mercury, during its calcination, absorbs the salubrious and respirable part of the air, or, to speak more strictly, the base of this respirable part, that the remaining air is a species of mephitis, incapable of supporting combustion or respiration, and consequently, that atmospheric air is composed of two elastic fluids in different and opposite qualities. As a proof of this important truth, if we recombine these two elastic fluids, which we have separately obtained in the above experiment, we reproduce an air precisely similar to that of the atmosphere and possessing nearly the same power of supporting combustion and respiration and of contributing to the calcination of metals. Similar results were obtained from experiments using phosphorus instead of mercury, but when he used nitric acid instead, the air produced was not fit for respiration and extinguished the flame. But when this air was combined in a ratio of 73 to 27 with respirable air, an elastic fluid precisely similar to atmospheric air in all its properties was formed. In the course of these experiments, Lavoisier noted that the terminology used to describe the different airs, that is, respirable, non-respirable, or noxious, were too vague, and thought that there should be better words to describe these ideas. So in 1787, Lavoisier got together with some of his contemporaries and presented to the Académie des Sciences a new system of nomenclature for chemical substances. We have already seen that the atmospheric fluid, or common air, is composed of two gases or aeriform fluids, one of which is capable by respiration of contributing to support animal life, and in it metals are calcinable and combustible bodies may burn. The other, on the contrary, is endowed with directly opposite qualities. It cannot be breathed by animals, neither will it admit of the combustion of inflammable bodies, nor of the calcination of metals. We have given to the base of the former, which is the respirable portion of the atmospheric air, the name of oxygen, from acidum, acid, and gignor, to produce, because one of the most general properties of this base is to form acids by combining with many different substances. The union of this base with what was formerly named pure or vital or highly respirable air we now call oxygen gas. The chemical properties of the noxious portion of the atmospheric air being hitherto but little known, we have been satisfied to derive the name of its base from its known quality of killing such animals as are forced to breathe it, giving it the name azot from the Greek privative particle alpha and vita, which means life. Hence, the name of the noxious part of the atmospheric air is azotic gas, which we now know as nitrogen gas in English. Lavoisier continued his experiments on airs by burning phosphorus in this apparatus, where he placed the phosphorus, or another metal, in this cup, and common air and oxygen were supplied via separate tubes. He then set fire to the phosphorus and found that its combustion was extremely rapid, being attended by a very brilliant flame and a considerable disengagement of light and heat. At the same time, the whole inside of the glass became covered with light white flakes of concrete phosphoric acid. He then measured the weight of the flaky residue produced in the reaction and found that it exactly equaled the sum of the weights of the phosphorus consumed and oxygen absorbed. Thus, the only action of the phosphorus is to separate the oxygen from the caloric, which is what they called heat, with which it was before united. This experiment proves in the most convincing manner that at a certain degree of temperature, oxygen possesses a stronger elective attraction or affinity for phosphorus than caloric, and that in consequence of this, the phosphorus attracts the base of oxygen gas from the caloric, which, being set free, spreads itself over the surrounding bodies. Similar results were obtained using charcoal and sulfur, but in the case of charcoal, the product of the reaction did not produce a solid but remained in the gaseous form. Lavoisier noted that these last three experiments may suffice for giving a clear and accurate conception of the manner in which acids are formed. By these, it may be clearly seen that oxygen is an element common to them all, and which constitutes or produces their acidity, and that they differ from each other according to the several natures of the oxygenated or acidified substances. It becomes extremely easy from the principles laid down to establish a systematic nomenclature for the acids. The word acid being used as a generic term, each acid falls to be distinguished in language as in nature by the name of its base or radical. Thus, we give the generic name of acids to the products of the combustion or oxygenation of phosphorus, of sulfur, and of carbon, and these products are respectively named the phosphoric acid, the sulfuric acid, and the carbonic acid. He also noted that there is a remarkable circumstance in the oxygenation of combustible bodies, and of a part of such bodies as are convertible into acids, that they are susceptible of different degrees of saturation with oxygen, and that the resulting acid, though formed by the union of the same elements, are possessed of different properties depending upon that difference of proportion. Of this, the phosphoric acid and more especially the sulfuric acid furnish us with examples. When sulfur is combined with a small portion of oxygen, it forms, in this first or lower degree of oxygenation, a volatile acid having a penetrating odor and possessed of very peculiar qualities. By a larger proportion of oxygen, it is changed into a fixed heavy acid without any odor, and which, by combination with other bodies, gives products quite different from those furnished by the former. And so, for substances that can be saturated by oxygen to various degrees, he suggested using the suffix "is" for the first or lesser degree of oxygenation and "ik" for the second degree. And so, for example, we get sulfurous acid and sulfuric acid. But for solid metals which don't form acids during combustion, but rather are only changed into intermediate substances, he proposed to rename the expression metallic calx, originally used not just for metals in this state, but to everybody which has been long exposed to the action of fire without being melted, to oxide, later changed to oxide. So, for example, iron oxide, which we also know as rust. Lavoisier also investigated the decomposition of water into carbonic acid, and for this he used this device here. First, he boiled some distilled water, which he had previously weighed, and passed the steam through this tube, EF, that went through a second furnace and out to a condenser, which condensed the steam back to water. Not surprisingly, he found that a certain quantity of water had passed over into the bottle, exactly equal to what was before contained in the retort, without any disengagement of gas whatsoever. But when he placed charcoal inside tube EF, which was heated by the furnace, he found that a considerable quantity of gas is disengaged, which he determined was composed of carbonic acid and a highly flammable gas, while the water that had condensed had lost weight compared to the starting quantity. He calculated that the amount of gas produced was equal to the water lost plus the charcoal burnt in the reaction, which suggested that the water and charcoal combined to produce carbonic acid and the flammable gas. When he repeated the experiment using iron instead of charcoal, he found that only flammable gas was produced and that the mass of the iron had actually increased by an amount equivalent to what was lost from the water minus the weight of the flammable gas, which indicated that the reaction was a true oxidation of iron by means of water, exactly similar to that produced in air by the assistance of heat. Thus, from these experiments, Lavoisier concluded that water is composed of oxygen combined with the base of inflammable gas, in the respective proportion of 85 parts by weight of the former to 15 parts of the latter. Thus, water, besides the oxygen which is one of its elements as it is of many other substances, contains another element as its constituent base or radical, and for this proper principle or element we must find an appropriate term. None that we could think of seemed better adapted than the word hydrogen, which signifies the generative principle of water, from aqua, water, and gignor, producer. We call the combination of this element with heat hydrogen gas, and the term hydrogen expresses the base of that gas, or the radical of water. This experiment furnishes us with a new combustible body, or in other words, a body which has so much affinity with oxygen as to draw it from its connection with caloric and to decompose oxygen gas. In this state of gas, hydrogen is about 1/13 of the weight of an equal bulk of atmospheric air. It is not absorbed by water, and it is incapable of being used for respiration without producing instant death. To confirm oxygen and hydrogen could be combined to form water, Lavoisier fitted a glass bottle with tubes connected to sources of oxygen and hydrogen, as well as a metallic wire having a knob at its extremity intended for giving an electrical spark, on purpose to set fire to the hydrogen gas. We next admit the oxygen gas as to fill the balloon and then, by means of pressure, force a small stream of hydrogen gas to which we immediately set fire by an electrical spark, and found that water was indeed produced in an amount that was equal to the quantity of oxygen and hydrogen admitted into the bottle. And so Lavoisier concluded that we may now affirm that we have ascertained with as much certainty as is possible in physical or chemical subjects that water is not a simple elementary substance, but is composed of two elements, oxygen and hydrogen, which elements, when existing separately, have so strong an affinity for caloric as to only subsist under the form of gas in the common temperature and pressure of our atmosphere. Therefore, the whole of Lavoisier's results effectively debunked the theory of phlogiston and ushered chemistry into a new age. Soon after the publication of his manuscript, Lavoisier died at the hands of the guillotine during the French Revolution, prompting a contemporary to say that it took them only an instant to cut off that head, and 100 years may not produce another like it. Although Lavoisier improved the terminology of chemistry in the 1700s, chemical symbols remained in the dark ages of alchemy and were found to be of very little utility, and owed their origin, no doubt, to the mysterious relations supposed by the alchemists to exist between the metals and the planets, and to the desire which they had of expressing themselves in a manner incomprehensible to the public. John Dalton's system of the early 1800s was a clear improvement over this, but it was Berzelius who would become a respected lawgiver, a veritable autocrat of the chemical laboratory, who saw the need for a new system of symbols to describe elements and molecules solely to facilitate the expression of chemical proportions and to enable us to indicate without long periphrases the relative number of volumes of the different constituents contained in each compound body. By determining the weight of the elementary volumes, these figures will enable us to express the numeric result of an analysis as simply and in a manner as easily remembered as the algebraic formulas in mechanical philosophy. So in 1814, he proposed that the chemical signs ought to be letters for the greater facility of writing, and not to disfigure a printed book. I shall take, therefore, for the chemical sign, the initial letter of the Latin name of each elementary substance. But as several have the same initial letter, I shall distinguish them in the following manner. 1. In the class which I call metalloids, I shall employ the initial letter only, even when this letter is common to the metalloid and to some metal. 2. In the class of metals, I shall distinguish those that have the same initials with another metal or a metalloid by writing the first two letters of the word. 3. If the first two letters be common to two metals, I shall, in that case, add to the initial letter the first consonant which they have not in common. Berzelius also proposed the use of superscripts, later changed to subscripts, to represent the ratio of each element in a molecule. So water, which is composed of two hydrogens with one oxygen, was represented as H2O, and the huge improvement this made can be seen with this example. This equation would have been used by Lavoisier to represent iron, water, oxygen, and nitrous oxide, whereas Berzelius and the rest of us could simply use this equation. But, as with anything new, some objected to this change, including Dalton himself, who said that a young student might as soon learn Hebrew as make himself acquainted with these symbols. Personally, though, I'm grateful to Berzelius and his symbols and happy that I didn't have to learn Dalton's. I will now switch over to the building blocks of elements, the atom, and more precisely to the electron, the discovery of which began with the study of electricity. The ability to store and release electrical energy at will only came about in the 1700s when the Leyden jar was invented. Simply put, this was a jar filled with a saline solution with a metal rod inserted into the lid. The jar was charged by repeatedly touching the rod with a generator of static electricity, and once charged could be discharged by touching the rod. But obviously a major disadvantage of this device was that only one charge could be stored, and so it had to be recharged every time it was used. The invention of the electric pile, or the battery, by Alessandro Volta in 1800 solved this problem. He placed pieces of silver and zinc 1 inch in diameter on top of each other, followed by a piece of cardboard soaked in salt water, and stacked these as tall as can be supported without falling over. When he tested a stack of 20 of these units, he found that it generated a slight commotion when the extremities were touched with wet fingers, similar to a Leyden jar except that it was continuous. And he found that the more units he added to the stack, the larger the electric shock was. So now with a constant source of electricity, real experiments could be conducted. So in 1834, the great Michael Faraday placed two metal plates inside a closed tube, connected each plate to the electrodes of an electrical source, and created the best vacuum he could inside the tube. When he did this, he noticed that the tube began to glow, and he called this radiant matter, although he had no idea how it was created. More than 20 years later, the German Julius Plucker repeated this experiment, but by now he was able to get a greater vacuum inside the tube and observed a green phosphorescence on the glass in the neighborhood of the negative electrode. But science being slow, it would be another 20 years before anyone could begin to make any sense of what was going on. So in 1879, William Crookes repeated these experiments using even more electricity in a tube that had been almost completely evacuated and noted that a dark space is seen to surround the negative pole, which is found to increase and diminish as the vacuum is varied. So he suggested that when electrical particles collide with gas molecules, it creates a glow. And Faraday saw a glow because he could only achieve a partial vacuum inside his tube. But Crookes suggested that if we exhaust the air or gas contained in a closed vessel, the number of molecules becomes diminished, and the distance through which any one of them can move without coming in contact with another is increased, the length of the mean free path being inversely proportional to the number of molecules present. The further this process is carried, the longer becomes the average distance a molecule can travel before entering into collision. We naturally infer that the dark space is the mean free path of the molecules of the residual gas. Consistent with this, he found that, in an increasing vacuum, the dark space around the negative pole widens out until it entirely fills the tube. If no residual gas is left, the molecules will have their velocity arrested by the sides of the glass, and here we come to the first and one of the most noteworthy properties of radiant matter discharged from the negative pole, its power of exciting phosphorescence when it strikes against solid matter. Interestingly, he found that a shadow was produced on the glass if an object was placed between the electrode and the glass. He also performed experiments using V-shaped electrodes and found that radiant matter only moved in a straight line and could not turn corners since the phosphorescence appeared at the bottom of the V-shape when generated at the top. Finally, he found that radiant matter could perform mechanical work since a paddle wheel would start turning when it was inserted in its path. Crookes then wondered what effect a magnet might have on radiant matter and found that the phosphorescence becomes curved under the magnetic influence, waving about like a flexible wand as he moved the magnet to and fro. The molecules shot from the negative pole may be likened to a discharge of iron bullet from a mitrailleuse, and the magnet beneath will represent the Earth curving the trajectory of the shot by gravitation. Interestingly, if the vacuum was decreased, he found that the path dips in the center towards the magnet. Here the action is temporary. The dip takes place under the magnetic influence. The line of discharge then rises and pursues its path to the positive pole. In high exhaustion, however, after the stream of radiant matter has dipped to the magnet, it did not recover itself, but continued its path in the altered direction. Crookes also built a tube with two negative electrodes on one side and one positive electrode on the other to determine if radiant matter carried a current, reasoning that if the streams of radiant matter carry an electric current, they will act like two parallel conducting wires and attract one another. But if they are simply built up of negative electrified molecules, they will repel each other. He found the latter to be the case. Given the results of his experiments, Crookes concluded, in studying this fourth state of matter, vapor, liquid, and solid being the other three, we seem at length to have within our grasp and obedient to our control the little indivisible particles which, with good warrant, are supposed to constitute the physical basis of the universe. We have seen that in some of its properties, radiant matter is as material as this table, while in other properties it almost assumes the character of radiant energy. We have actually touched on the borderland where matter and force seem to merge into one another, the shadowy realm between known and unknown, which for me has always had peculiar temptations. I venture to think that the greatest scientific problems of the future will find their solution in this borderland and even beyond. Here, it seems to me, lie ultimate realities, subtle, far-reaching, wonderful. Scientists continued to study the strange matter which, by the end of the 1800s, had been named cathode rays. J.J. Thomson commented that, according to the almost unanimous opinion of German physicists, cathode rays are due to some process in the ether to which no phenomenon hitherto observed is analogous. To address objections that radiant matter was made up of negatively charged particles, Thomson used this apparatus, with a cathode and an electrometer to detect and measure charges when they could make their way through the slit. By using a magnet to change the path of the radiant matter coming off of the cathode, Thomson found that a charge on the electrometer was only detected when the path of the rays was deflected to make it go through the slits, thereby showing that this negative electrification is indissolubly connected with the cathode rays. Thomson also designed a tube in which cathode rays pass between two parallel metal plates before falling on the anode, where a scale was pasted on the glass to measure the angle of deflection of the ray exerted by the electrified plates. He initially got the same results as others, that is, that electrostatic forces had no effect on the ray, but he also found that the absence of deflection was due to the conductivity conferred on the rarefied gas by the cathode rays, and showed that increasing the vacuum inside the tube decreased this effect to such a degree that the rays were deflected when the two aluminum plates were connected with the terminals of the battery of small storage cells. Therefore, Thomson concluded that, as the cathode rays carry a charge of negative electricity, are deflected by an electrostatic force as if they were negatively electrified, and are acted on by a magnetic force in just the way in which this force would act on a negatively electrified body moving along the path of these rays, I can see no escape from the conclusion that they are charges of negative electricity carried by particles of matter. The question next arises, what are these particles? Are they atoms or molecules or matter in a still finer state of subdivision? To begin answering these questions, Thomson used a variety of methods to calculate the mass-to-charge ratio of the particles and determined that they were way smaller than that of the hydrogen ion during electrolysis, which had the smallest known mass-to-charge ratio. What Thomson had found was the electron, the negatively charged particle of the atom, and this implied that positively charged particles, later called protons, must also exist in atoms since atoms were known to be electrically neutral. So in 1904, Thomson proposed the plum pudding model of the atom, in which the atoms of the elements consist of a number of negatively electrified corpuscles enclosed in a sphere of uniform positive electrification, similar to the plums in plum pudding. However, the same year, Hantaro Nagaoka in Japan proposed an alternate hypothesis which proved to be correct, the planetary model of the atom, in which electrons revolve around a massive nucleus of protons and were held together by electrostatic forces. Even by the early 1900s, very little was known about how the different atoms and molecules were held together, but in 1916, Gilbert Lewis suggested that atoms are composed of a core of protons and electrons with an outer shell containing a given number of electrons, which varied depending on the element in question. And Lewis proposed that all atoms strive to have a complete outer shell filled with 8 electrons, such that atoms have a tendency to donate, accept, or share electrons in an effort to total 8 outer shell electrons. For example, sodium only has 1 electron in its outer shell and chlorine only has 7. And so the most stable configuration for both these atoms would be for sodium to lend an electron and for chlorine to borrow one, which can be accomplished by the association of these elements, and we know this as table salt, where chlorine borrows an electron from sodium. Water, on the other hand, has atoms that associate by covalent bonds, which means that electrons are shared between the atoms, and this makes these molecules more stable. It should be noted here that hydrogen is an exception to the 8-electron rule, since it only has 1 electron in total, so it only needs 2 electrons to be stable. So the 2 hydrogen atoms in water share their electron with oxygen, and oxygen shares 1 electron with each of the hydrogens, giving hydrogen 2 electrons and oxygen 8 electrons in their outer shell. Lewis also introduced a new form of chemical symbols that bears his name, the Lewis structure, to easily visualize the phenomenon of electron sharing, which uses colons to represent the 2 electrons which act as the connecting links between the 2 atoms. For example, water is represented by this, and we can see how these 2 electrons are shared between oxygen and this hydrogen, and similarly these 2 electrons are shared between oxygen and this hydrogen. In 1939, the American Linus Pauling published his seminal The Nature of the Chemical Bond, where he brought to the masses the concept of hydrogen bonds, which would eventually be shown to be one of the most important bonds in biology. When atoms share electrons during the formation of molecules, the molecule becomes a dipole, meaning that certain parts of the molecule become more negative than others, and we call this electronegativity. So again, using water as an example, the area around the oxygen atom is more electronegative than the part around the hydrogens because there are more electrons in that area. So if two water molecules are close to each other, the electronegative oxygen of one molecule and the less electronegative hydrogens from neighboring molecules would be attracted to each other. And these hydrogen bonds are one of the main reasons for the striking physical properties of this uniquely important substance, referring to water. When water freezes, water molecules are so close to each other that every hydrogen atom is in hydrogen bond with the oxygen from a neighboring water molecule. The hydrogen bond's been shown to be one of the most important bonds in biology, despite the fact that, and actually because of the fact that its bond strength is very weak, which makes the energy required to make and break hydrogen bonds very low, and so this bond is especially suited to play a part in reactions occurring at normal temperatures. And as I'll discuss in the videos on the discovery of DNA and proteins, hydrogen bonds are instrumental for the maintenance of their structure. And so this brings this video to an end. I hope you enjoyed it. And if you did enjoy it and would like to know more about the history, please check out my book using the link in the description. And if you have any questions on this video, please leave them in the comments and I'll do my best to answer them. And I hope you'll join me for the next video on the discovery of cells and genetics.